Hello everyone, I am Dr. Mohammad Haris Amayo, Chemical Engineering faculty member and an Aspen Tech certified user. Welcome to this lecture series on machine learning for chemical engineers. Machine learning is transforming the way chemical plants are designed, operated, optimized, and controlled. In this lecture, we will explore the first and most widely used category of machine learning, which is supervised machine learning, with a special emphasis on its applications in chemical engineering. By the end of this lecture, you will be able to understand what supervised learning is, how it works, where it is used in chemical engineering, and why every modern chemical engineer should understand this technology. So let's begin. For decades, chemical engineering relied heavily on first model principles. These models are based on the fundamental laws of physics and chemistry, including mass balance, energy balance, momentum balance, reaction kinetics, and thermodynamics. They remain extremely valuable. However, modern industries now generate enormous data which is generated every second. Thousands of sensors continuously record variables such as temperature, pressure, flow, composition, liquid level, and equipment conditions. Instead of manually deriving every equation, machine learning enables computers to learn directly from historical process data. Rather than asking what equations describe this system, we now ask what patterns exist in the data. This represents one of the biggest paradigm shifts in modern process engineering. Today's models don't just simulate a process, they can learn, they can adapt, and they can predict future plant behavior. Interestingly, artificial intelligence is not new to chemical engineering. Back in 1980s and 1990s, researchers developed what are known as expert systems. These systems use thousands of if-then rules. For example, if reactor temperature exceeds a certain limit, then reduce the feed rate. Several successful systems emerged during that era. Examples include Confide for thermodynamics, DSVL for distillation design, and DKIT, which was developed in 1993. Although these systems demonstrated promise, they never became mainstream. Why is that? Because the computing power, storage capacity, and process data available at that time were extremely limited. In many ways, the industry was nearly 20 years ahead of the available technology. Today, cloud computing, big data, and powerful processors have finally made intelligent systems practical. Now, talking about the supervised learning, this is a machine learning technique in which a model learns from labeled data. A labeled data consists of the input variables and the correct output associated with those inputs. Think of teaching a student. You give the student many solved examples. Eventually, the student learns the relationship and can solve new problems independently. Machine learning works exactly the same. For example, suppose we have data consisting of reactor temperature, pressure, catalyst concentration, feed flow rate along with the corresponding product yield. The algorithm will learn the relationship between these variables. Later, when presented with the new operational conditions, it predicts the expected product yield. Now, this consists of three steps. Number one is collection of historical process data. Number two, training of the machine learning model. And number three, using the trained model to predict the new outcomes. One of the most famous benchmark problems in chemical engineering is Tennessee Eastman Process, which is commonly called as TEP. It simulates a realistic industrial chemical plant consisting of reactors, compressors, separators, recycle loops, and numerous interacting process variables. Because of its complexity, researchers worldwide use TEP to evaluate new fault detection and control algorithms. Traditionally, plants relied on alarm system. An alarm only activates after a process variable has exceeded a predefined limit. Supervised learning has obviously changed this thing. Instead of waiting for alarms, it detects subtle patterns that indicate an upcoming fault, enabling operators to take corrective action long before serious process disturbance occurs. An important application of supervised learning is anomaly detection. Historically, engineers relied on techniques like principal component analysis, or we can call it as PCA. It works well for processes exhibiting mostly linear relationships. However, modern refineries and petrochemical plants exhibit highly non-linear behavior. The deep learning models, particularly autoencoders, which are represented here, are capable of learning these non-linear relationships. Studies have shown that deep learning models can identify equipment failures 1 to 2 hours earlier than the conventional monitoring systems. This additional warning time can significantly reduce downtime, maintenance costs, and safety risk. However, there is a trade-off that deep learning requires much larger data set and greater computational resources. Now, looking at the practical applications of the machine learning, number one is heat exchanger fouling. As fouling develops, we know heat transfer efficiency gradually decreases. Supervised learning models analyze sensor data and predict fouling progression before severe performance losses occur. Another important aspect is distillation column optimization, that machine learning models continuously analyze plant conditions and recommend operational parameters, which include reflux ratio, feed rate, and operating pressure. As a result, plants achieve higher separation efficiency, reduced energy consumption, and increased production rates. These are no longer academic studies. Many of these systems have already been implemented successfully in industry. Machine learning is also revolutionizing the molecular design. Traditionally, discovering a new catalyst or solvent required thousands of laboratory experiments and consuming years of research effort. Today, these models predict relationship between molecular structures and material properties. Instead of experimentally testing every candidate, researchers first screen thousands or even millions of molecules computationally and then applying or then proceeding with the promising candidates. Despite all these applications or all these exciting developments, machine learning presents important challenges. Number one is the black box problem, that things are not reflected or not interpretable by the engineers. Second is the skill gap, that future chemical engineers must understand both traditional engineering principles and modern data science techniques. And finally, machine learning models must always remain physically meaningful. Machine learning should complement engineering knowledge, not replace it. Now, looking ahead, chemical plants will become increasingly intelligent. Deep learning systems will monitor millions of variables simultaneously. They will optimize plant performance in real time, predict equipment failure, reduce energy consumption, and improve sustainability. However, the engineer will remain at the center of decision making. Machine learning is a powerful engineering tool, not a replacement for engineering judgment. The future belongs to the engineers who combine domain expertise with artificial intelligence. So that's it from this lecture. Thank you for watching this lecture. In the next lecture of this series, we will explore unsupervised machine learning and see how algorithms can discover hidden patterns in chemical process data without required labeled data sets. If you found this lecture helpful, please like the video, subscribe to the channel, and share it with fellow engineers and students interested in AI and chemical engineering. I am Dr. Mohammad Haris Humayun. Thank you, and I will see you in the next lecture.